Greetings. My name is Lawrence Johnson, and this will be an overview of Hierholzer's algorithm. Hierholzer's algorithm has a primary use case for finding Euler trails and circuits in graphs, provided that these graphs are connected. A Euler trail is a walk traversing the graph using each edge only once. A circuit is the Euler trail with the same initial and final vertex. So if we have a connected graph, we can find a Euler trail and a Euler circuit if they exist, as long as we have a few conditions on the graph. Now, if you have all even vertices in these planar graphs, that say your graph is given to be planar, and we can find a Eulerian trail. Hierholzer's algorithm helps us to find this, and was actually a way to improve upon the work previously done by Fleury's algorithm when finding Eulerian circuits. Hierholzer's algorithm, however, is a lot more efficient. It's linear with respect to the edges in terms of the computational complexity time. When implementing the Hierholzer's algorithm, one may use a linked list for the set of unused edges, and then another link to store the set of edges. Each time you go from one vertex to another, you remove an edge, you replace that edge, or you record that in the first list, basically like a ledger. Then you go to the next and the next until you remove that loop. Then you go to the next. Let's take an example. With this graph, we have 8 vertices. I'm taking the liberty to go ahead and just highlight where the Eulerian circuit is. If you go from 1 to 3 to 2 and 6 and 5, 7, 4, then 8, 5, 4, 2, and 1, you can traverse the graph without repeating any of the edges. Okay. Let's say we use the algorithm now. We will go through a series of removal of the edges and adding into our ledger as we remove the loops. Until it's disconnected. All right. Okay. With this being our initial graph, we can perform the first few steps of the Hierholzer's algorithm. Removing the 3 as we go from 1 to 3 to 2. We could go back to 1, and that's the bottom triangle. All right. But then by taking that last element off and then putting that into the next vector, and then going from 2 into our next situation, where we remove the cycle from 2 to 6 to 5, 4 to 2. Right. And then we pop off that second one. That goes into the other vector as well. we get through that last cycle. And we take that one off as well. Once we put the cycles together, we find that the walk 1, 3, 2, 6, 5, 4, 8, 5, 7, 4 will traverse the graph. Keep in mind how this cycle is formed based off of the orbits of these cycles from before. 1 goes to 3, 3 goes to 2. A 2 is 1 to 6 in this next one. 2 goes to 6, 6 goes to 5, 5 goes to 4. 4 goes to 8 here. 8 goes to 5, 5 goes to 7, 7 goes to 4. And we complete the cycle. Well, we will traverse the graph. The data on the back end can be used is using linked lists. But I saw this as a visual way, a geometrical way of showing how to basically take these polygons to decompose our graphs using Hierholzer's algorithm to find Eulerian trails within graphs under the proper conditions. Peace.